Put forward over the course of the latter half of 1927 through a series of conference presentations and papers, the Copenhagen interpretation was the attempt of Niels Bohr, Werner Heisenberg, and Wolfgang Pauli to bring together the work of a small group of mostly German physicists on understanding quantum theory in a set of coherent statements from which further work might proceed. It was the culmination of the picture Heisenberg had first put forward in his 1925 formulation of matrix mechanics, along with Bohr's continuing attempts to understand wave-particle duality, something put forward initially in Einstein's paper on the photoelectric effect in 1905, but brought to the forefront of quantum thought in the recognition by Louis de Broglie that electrons, and indeed all subatomic particles, must display both behaviors depending on how they are measured. The interpretation, most forcefully enunciated at the Fifth Solvay Conference by Max Born and Heisenberg, laid out the stakes of how the main research group involved in understanding the atom would consider the issues. This group, through traditional methods of professional exchange, would end up having the greatest impact on the growing community of physics in the United States, where, after the war, the great advances towards a unified field theory and a standard model would be made. While not agreed upon by everyone at the time, or even now, it is the dominant scientific and philosophical statement about what quantum mechanics means and how it works.
Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a many-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery.
Series 2, A History of the Atom. Episode 16.4, Supplemental, the Copenhagen Interpretation. I wanted to break out a specific supplemental episode on this topic for a few reasons. First, as this interpretation of quantum theory will do much to define the path forward, I thought it would be good to make sure it was clearly and concisely stated. Second, since I have neglected some of the philosophical issues related to atomism in general and the specifics of the atomic models going forward from Bohr, I felt that it was time to at least clean up a bit of that. Finally, to be honest, I still need a bit more time to do the research related to Heisenberg's involvement in the Nazi regime. And this episode will serve a purpose of filling in some space as I wade through that research while also providing that needed information for the later episodes. So as they say, two birds. Or in this case, maybe three. Now, when a student studies quantum mechanics as part of a physics, chemistry, or in rare cases electrical engineering major, he or she usually focuses on the technical details of it all. Over the course of 2 or 3 classes as an undergrad, they will learn how to solve certain standard problems using Schrödinger's formulation of quantum mechanics, the method of waves, and possibly they'll be introduced to Heisenberg's more complicated matrix mechanics, but not at a very deep level. If they continue on to graduate school, in their first year of study, they'll look at Heisenberg's work in detail, as well as learn about Dirac's formulation of that approach with all of its mathematical elegance. And at the end of the course, they'll probably be introduced to some relativistic effects and field methods. Now, if the student wishes to specialize in something like particle physics or certain areas of what is known as condensed matter physics, they will take a second level of graduate classes on quantum field theory. The point of these classes, in most cases, is to teach the student the technical details of using the tools to model and understand the physical systems. Unless a professor takes the time, the important philosophical implications of the work are sort of left to either more general treatments discussed in the first sophomore level class, chatted about in informal meetings and faculty-student interactions, or, far too often, just neglected entirely. I think that Bohr would have been a bit horrified by this sort of approach to the education, especially given the level of importance he placed on clearly defining the ideas of the work that Heisenberg, Pauli, and he had done, often very contentiously, to understand what was being said. So before we move any forward in the series of the podcast, I think we should lay out very directly what the Copenhagen interpretation said about quantum theory. The ideas that will follow here are adapted from a lecture given by Dr. Catherine Carson at the University of California at Berkeley for her class, History 181B, Modern Physics. It's a great class. It's available through iTunes U, and if you really would like to dig into sort of the development of modern physics in the 20th century, I can't recommend it highly enough. So, what is the Copenhagen interpretation? Well, it rests on three foundational ideas: Heisenberg's uncertainty principle, Max Born's interpretation of the meaning of Schrödinger's wave function, and Bohr's complementarity principle. Let's take a look at each of these in turn. The uncertainty principle is derived from Heisenberg's 1925 paper on matrix mechanics. As you will recall, one of the results of that paper, something confirmed by Paul Dirac shortly after, was that when a person multiplied the position of something by the momentum of that thing, the order in which the multiplication takes place matters. From this, Heisenberg was able to show mathematically in a 1927 paper that this meant that there was a limit on how accurately you could measure these two quantities at the same time. To review just a bit more, in classical physics, position is where an object is in space. Now, more generally, position actually is said to be where an object is in space-time. The trickier thing to understand, however, is momentum. Again, in classical physics, momentum is the product of an object's mass and its velocity, which can also be said to be how the object's position in space is changing. When you generalize momentum, though, it gets a bit trickier as the definition of mass becomes more technical. For a physicist, mass is that property of an object that resists a change in the object's motion, or, put another way, an object's mass is sometimes called inertia, as it reduces the amount of acceleration an object will experience when a net force is applied to it. What Heisenberg shows is that you can't measure both an object's position and its momentum at the same time with infinitely great accuracy. Now, this is counterintuitive when thinking about things that we sometimes call being on the macroscopic scale, i.e., stuff we can see, or what my philosopher colleagues like to call medium-sized dry goods. When you go to a baseball stadium, a camera sure seems to be able to measure both the position and the momentum of the ball pretty accurately. The problem with this sort of understanding is twofold. First, the camera in this case is not really measuring either position or momentum with all that much accuracy, at least not compared to the types of numbers Heisenberg wants to think about. If the camera and radar gun can measure the position of the ball within, say, 1/millionth of an inch and 1/millionth of a mile per hour, to use some old school units, something that would be pretty remarkable given the technology, that's still about 10 to the 20th times less accurate than Heisenberg's actual limit of measurement. Second, the baseball consists of about 10 to the 25th number of subatomic particles, the kinds of things Heisenberg is really talking about with his uncertainty principle. To understand the bulk motion of all of these particles together, one has to take a bunch of statistical averages, which is something we'll see if we can come back to later when we talk about Born and the wave function. What this means is that you have to let go of thinking about stuff you can see with your eyes and try to confine your consideration to those things that are smaller than atoms, and then consider measuring the position and momentum of that kind of a system. In order to do this, you have to consider how you might actually measure the position of something that tiny. To illustrate, let's take Heisenberg's example of measuring the position of an electron. To do this, you have to have the electron interact with a photon of light, because that's how we see things. the wavelength of this photon has to be on the order of the position you want to measure. For baseballs, this can be pretty big, millions of times the wavelength of visible light. But for an electron, the wavelength has to be really, really small, on the order of the wavelength of a gamma ray photon. However, as the wavelength of the light gets smaller, the energy of the photons that make up the light, the energy they carry, gets a lot bigger. So, what you're going to try to do is shoot a photon with a whole lot of energy, and thus a whole lot of momentum, at the electron you're trying to find. If the photon interacts with the electron, you'll know where the electron is, but the interaction of the photon's momentum with the very lightweight electron will really change the electron's momentum, and so you won't have a good idea of how the electron will be moving after that interaction. The better you want to know the electron's position, the smaller the wavelength of the photon has to be, and the more it will change the electron's momentum. Now, there are some additional technical details to this thought experiment, known as Heisenberg's gamma ray microscope, that I've left out of this example, but it does a pretty good job of illustrating what the mathematics demonstrates is actually going on with the uncertainty principle. So, what are the consequences of this result? The first is to call into question whether one can actually say if these microscopic entities, things like electrons, have both defined position and defined momentum at the same time. Whenever someone tries to extract information about these two variables at the same time, they can't get at the information about them simultaneously. As Carson says, quote, "When we talk about the microscopic world, there's going to be an intrinsic limitation on our information about it. If you know one thing about it infinitely precisely, you're going to inevitably know nothing about the other. In fact, you could even come to say that it does not seem to be true that microscopic objects like electrons have both clearly specified positions and clearly specified momenta at the same time." Unquote. The second thing is that Heisenberg says that we can't actually talk about the electron's position as such. All we can really talk about is that we measured it to be in a given position. To talk about the position as if we know it absolutely assumes that we have the perfect information the uncertainty principle explicitly states we can't get at. All we can really say is that when we went looking for the electron at some point in time using a specific piece of equipment, we found it at a specific location with a certain uncertainty in the measurement. This means, and this is really pretty important for some of the points we'll be making down the road in a bit, we have to be explicit and precise in describing the experimental setup we used to make our observation. Changing the apparatus we use to measure things about a system will have important consequences to what we actually end up being able to measure. Third, and this is probably the most important consequence of Heisenberg's ideas in the big picture, he specifically states that the uncertainty principle has very important and fundamental consequences for what is known as the law of causality. Now, discussions and well thought out philosophical positions about the law of causality date back to at least Berkeley and Hume in the European philosophical tradition. But in the sciences, the best sort of explanation dates to a mathematician by the name of Pierre-Simon Laplace. While it is clearly assumed in Newtonian classical mechanics, it is Laplace who explicitly states that if, quote, one knows the exact position and momentum of a particle at a given instant, along with all of the forces acting on the particle, then one can use Newton's laws of motion to calculate the particle's exact position and momentum at any given future instant, unquote. What Heisenberg is saying, as I mentioned in the second mathematical atom episode, is that while the causality relationship might indeed hold true, since it is impossible to know the exact position and momentum of a particle at any given instant, one can't actually calculate those quantities at some later time. Thus, in the microscopic world, the law of causality will never actually apply. Moreover, and this is really for the philosophy nerds out there, This forces a redefinition of Kant's a priori ideas on underlying physical truths based on human perception. In other words, while such a priori truths might indeed exist, they can't be based on the idea of strict physical causality, at least in the microscopic world. Heisenberg says that Kant's argument that we can't structure perception in such a way that it violates cause and effect must be revised to account for the fact that we can't know about the cause with ultimate or infinite accuracy at the microscopic level. Now, I don't know about you, but I think this is some pretty profound stuff. Of course, we have a sense of cause and effect at the macroscopic world. But what this means is that there has to be some way of bridging from the uncertainty of things like subatomic particles to the certainty of a car moving down the highway at a given speed, in a given direction, under the influence of known and understood forces. Here is where one final point should be made about what the uncertainty principle is saying about the availability of information. In the example of the car, we may not know whether it will be able to stop the car in time if a child chasing a ball were to run out into the road in front of the car. That lack of knowledge, however, is because we may lack some vital piece of information, say the stopping force of the brakes or the mass of the vehicle or something like that. But it's not because we can't know that information. We could conceivably take the vehicle into some test environment with all the standard equipment and run a bunch of tests on the vehicle in order to determine the things like the force of the brakes that will be applied and that kind of a set of stuff. Additionally, with a few tools such as a radar gun and a high-speed computer, we could determine whether the car will hit the child before it actually does and advise whether evasive maneuvers would be necessary. In fact, with their faster reaction times and processing speeds, this is one of the real advantages of autonomous vehicles. In this case, the limitation on our predictive ability is either a simple lack of knowledge or an unwillingness to get at it. With the uncertainty principle, Heisenberg is saying that we can't get at the information, and thus we can't predict what will happen for a single electron in the future. If we were to try to apply the principle unrealistically to the car, we wouldn't be able to tell if the car was going to hit the child because we'd either know where the car was, but we'd have no way of knowing anything about how fast it was going, or we'd know the speed and direction of the car's motion, but not where it was at a given time. This, of course, is not an appropriate application of the uncertainty relationship, as we can know both of these things about something the size of a car without much difficulty. The question, therefore, becomes, how do we bridge between the two realms? The microscopic realm, where the uncertainty principle applies, and then the macroscopic realm, where it doesn't. This is where the paper published by Max Born shortly after Schrödinger put forward wave mechanics comes in. While Schrödinger thought that his wave function, psi, represented some sort of electron density wave in space, Born pointed out that the wave function had to be what mathematicians call complex, meaning that it has the square root of -1 in it somewhere. This is something that real waves in space, things like water waves or waves on a slinky, don't have. Instead, Born pointed out that Schrödinger's waves seem to be in something physicists call configuration space rather than the normal three-dimensional space we all perceive. What Born was able to show was that if you took the imaginary wave function of Schrödinger and squared it, you get the probability of finding an electron at any given position around an atom if you were to try and make a measurement. Now, an analogy is useful here. Let's say you have a single six-sided die. If you were to consider rolling that die, you wouldn't actually know what the outcome was going to be. But you would know that the probability of any particular number coming up is 1/6, or about 16.6%. Now, if you roll a whole bunch of dice, what that means you can do is you can get a pretty good idea of the number of those rolls that will come out with a specific result. So, if I were to roll 1,000 dice, I get about 166 ones and 166 twos and so forth. If we were to change the experiment a little bit and we were to do it with 2 dice, you'd have a different set of probabilities. Since you'd have a 1 in 36 chance of rolling a 2, or snake eyes as they say in Vegas, a 2 in 36 chance of rolling a 3, a 4 in 36 chance of rolling a 4, and so forth. Again, while you couldn't actually predict what the roll will be prior to throwing the dice, you know that if you were to make a large number of measurements, i.e. roll a large number of pairs of dice, you'd be able to predict fairly accurately what the number of each outcome would be. Since macroscopic systems always have enormous numbers of subatomic or atomic particles, the statistical averages will always end up producing the predictable behavior we see there. That's at least what Born's going to say. It's what he calls his probabilistic interpretation of the Schrödinger approach to understanding atomic processes. Now, this approach predates Heisenberg's work, as it was done in late 1926-1927, but it's an important thing that leads to the corporate Copenhagen interpretation. It's clearly incorporated into the thinking of the group fairly strongly by the time of Heisenberg's 1927 paper, and thus serves as a way to bridge from the microscopic environment where causality and determinism do not hold to the macroscopic picture where they certainly seem to. The third key idea of the interpretation is what is known as Bohr's principle of complementarity. As an initial statement of this final piece, I like to quote Dr. Carson directly from her lecture titled Making Sense of Quantum Mechanics. Quote, "It is the assertion that to understand these strange phenomena, it is necessary to use mutually exclusive sets of classical concepts. You have to use wave pictures for some things and particle pictures for some things. You need both of them to describe certain situations physically, but you never need both at the same time." Unquote. What Bohr is doing with this is really generalizing Heisenberg's idea about as far as you can. Position is very much a particle idea, while momentum, at least in the more generalized way it's being used by this time, is something more applicable to waves. What complementarity is saying is that if you look at a system with an apparatus designed to probe its particle nature, you will retrieve particle information at the expense of wave information. On the other hand, if you look at a system with an apparatus designed to measure a quantity like momentum, you'll extract wave information, but only at the expense of knowing anything about the particle information. Therefore, if a scientist wants to fully describe a quantum system being studied, he or she must obtain information using different types of complementary apparatuses designed to measure the differing types of information about the system. Now, this sort of complementarity can apply to many different things about the system. It can apply to what are known as conjugate variables, 2 of which we know to be the position and momentum, though there are others we'll describe in a later episode of the podcast. It can apply to the issue of wave-particle duality. It can apply to the experimental apparatus being used, i.e., when one does Young's double-slit experiment, light shows wave behaviors, but when one does photoelectric effect investigations, light shows particle properties. So, where the philosophy comes in here is that Bohr says that you have to do things in this way in order to fully understand quantum systems. You can't think something like, okay, well, neither the wave picture of light nor the particle picture of light works to explain both experiments, so what I'll do is I'll come up with some way of combining the two that can explain them both. This is what Einstein had tried to do with his publication on the photoelectric effect, and while it seemed to offer a road forward there, the idea quickly broke down. What it comes down to is that you can't actually have something that's both a particle and a wave at the same time. What you can do, though, is you can say that light has wave properties when we look at it in this particular way, then it has particle properties when we look at it in that other different particular way. There's no way around this type of description, Bohr says. What he points out is that due to our actual sensory perception being limited to the macroscopic world, we're limited to the classical physics descriptions that grow out of that perceptual limitation. While the mathematics may be able to create predictive models, it cannot help us understand the system in a way that our everyday experience will contextualize for us very well. Thus, we must use both the complementary classical pictures, i.e. particles and waves, to explain the behavior of a system because these are the classical macroscopic descriptions of things that we have. In other words, in the regular old world we interact with every day, you either have bullets traveling in trajectories through space or undulations moving through a slinky. So when talking about these microscopic things that are so different than the big macroscopic stuff, we have to use these kinds of classical descriptions and use them all to be able to fully arrive at the sense of what the behavior of the microscopic system is. As these ideas are brought together in 1927, they are sort of compiled by Heisenberg and Born under the guidance of Bohr for presentation at the 5th Solvay Conference. If one goes out and searches on the Copenhagen interpretation, it's not hard to find a list of supporting conjectures that arise from the three pieces that we've talked about that form a pyramid. Born's probability interpretation of Schrödinger's wave function in late 1925, Heisenberg's uncertainty principle in late 1926, early 1927, and finally, Bohr's principle of complementarity, presented most fully in the summer of 1927 at a conference in Italy. Let me work from a list that Dr. Carson sort of put together of conjectures, and I'll add a couple of things to sort of summarize what the outcome of the interpretation was. First, it's important to understand that quantum mechanics generalizes classical mechanics rather than discarding it entirely. Second, there is this thing known as a wave function that represents the state of the system. It exhausts what can be known in advance of observation about a particular occasion of the occurrence of a system, and beyond it there are no quote-unquote hidden parameters. The description of the system given by the wave function is probabilistic. Third, when thinking about the generalized classical ideas, things like position and momentum, one must also think about how they are operationally realized. Another way of saying this is that one must be fully aware of how these things are going to be measured in real experimental setups. Fourth, if you accept Heisenberg's uncertainty principle as the mathematical result or outcome of the commutation relationship he derives when coming up with matrix mechanics, then you have to give up the idea that strict causal prediction and determinism are possible on a microscopic level. Fifth, as a corollary to this fourth point, Heisenberg asserts that the observer, or at least the observer's choice in measuring instrument, affects the system through interfering with it. Sixth, in the principle of complementarity, you have the statement that to understand a system, you are limited to classical descriptions of which you must use mutually complementing descriptions to understand the full quantum system. Finally, seventh, in what is known as the strong position or interpretation, Bohr says that you can't get past this description of the nature of quantum systems. In other words, there isn't going to be some better theory down the road that will allow you to return to purely classical descriptions of things, or that doesn't require uncertainty, a probability-based interpretation of quantum behavior, and a need to use complementary classical descriptions of a system's behavior to fully account for the quantum nature of subatomic particles. As I close this podcast, there are a few historical footnotes and caveats that should be made about this interpretation. The first is that it wasn't called the Copenhagen interpretation until much, much later than when it was first proposed. Heisenberg refers to the, quote, spirit of Copenhagen, unquote, in a textbook he wrote in 1930, but the actual term doesn't arise until the 1950s. This is because the use of the term suggests that it's only one of several different ways to interpret the quantum picture, something Heisenberg specifically rejected. To him, and indeed all of the collaborators in this group, the question was settled in 1927 with little or no additional work being needed. The second point to be made here is related to the first. While the men and women working in the network associated with Bohr and Copenhagen accepted these ideas, there were those who did not, namely Einstein, who rejected Born's probability interpretation, and Schrödinger, who fundamentally disliked the discontinuous nature of Heisenberg's stationary states and quantum jumps. Add to these two Max Planck, Louis de Broglie, and a physicist by the name of David Bohm, and you have a small but influential group of talented physicists who feel that they're outside of the mainstream both scientifically and socially. At stake here isn't just a description of how quantum systems work, but also what science is and how science is done. For Einstein in particular, the fact that the Copenhagen interpretation put very real limitations on our knowledge about physical systems was troubling. As Carson says in her lecture, quote, Einstein says that science is not supposed to be about what we can and can't know, but rather about the physical world and not about what's going on inside our heads, unquote. One of the questions that can be raised in relationship to quantum mechanics is whether one can have a proper scientific theory when it can only make probabilistic predictions about the states of systems. In other words, does science require a sort of determinism in its hypothetical process? Does such an examination undermine one of the assumed basic functions of scientific inquiry, coming up with causal connections between things in nature? Einstein says that when you abandon deterministic causality, as the Copenhagen interpretation requires that we do on the microscopic level, you abandon one of the fundamental reasons something like science exists in the first place. Following on this, is it okay to have a scientific theory that only gives complementary descriptions? Shouldn't you have a theory that gives a single, unified description of a system and its behavior? Isn't that also one of the fundamental goals of science? The big accomplishment of 19th century science in many cases is to be able to come up with a single framework under which all phenomena can be accounted for. In physics, that's the great triumph of Newtonian mechanics coupled with Maxwell's electromagnetic theory. Finally, there are questions to be raised regarding objectivity. If, in some sense, the observer becomes part of the system by choosing a measurement apparatus and procedure, does this undermine scientific inquiry in some way? For Einstein, the single most crucial aspect of science is that it comes up with descriptions of the natural universe that are independent of us. Einstein's criticism of the entire endeavor is that if you have a theory that sacrifices causality, unity of description, and objectivity, then the theory can't really be said to be scientific, and thus it cannot stand as an end of the discussion. For him, this means that there must be some other theory that will not make these kinds of sacrifices that has not, as of yet, been arrived at. The third point that I'd like to make is that the Copenhagen interpretation will become the dominant theoretical and philosophical position of physics in the United States from the 1930s through at least the 1980s. This is a result of the fact that through the numerous American foundations supporting the work done in the institutes focused on this research, a number of very talented individuals from the United States traveled to Denmark and Germany to study under the men who put this picture together. Furthermore, as the Nazis came to power, first in Germany and then more widely throughout Europe, a number of the scientists there fled to the United States where they would train the next generation of students. This, however, is not to say that this was the only interpretation of the data, or, at present, even the dominant interpretation of the data. There were other ideas put forward, most notably by Einstein and those gathered around him, in questioning the Copenhagen group. As we'll deal with Einstein's specific objections and attempts to offer alternative explanations in greater detail in a later podcast, I'll leave it to say that most of the effort put forward by this group centers around what are known as hidden variable interpretations. In this view, it is the idea that it is the strong position, point number 7 that I mentioned before, of the Copenhagen interpretation that is wrong. It is not the last word, but rather there is something, a hidden variable as it were, which hasn't been observed or accounted for when it comes to quantum systems. This unobserved factor, thereby, is said to give rise to the perception of probabilistic behavior and uncertainty. But once it is understood, it will collapse the descriptions of the system to something both deterministic and objective. In the last 3 decades, a new view known as the many worlds interpretation has gained a large number of adherents. In this interpretation, each time there is an outcome for a process that is determined via probability, there is a new universe spawned that contains that outcome. To use our die example from earlier, when you roll the die, there are 6 universes that arise from that event, one each for each possible outcome of the roll. This interpretation has gained a number of adherents in the last 2 decades, not the least of which include a few prominent Hollywood storytellers and some sort of an incomprehensible island or something. At least that's what I'm told. While recent surveys suggest that somewhere around 40% of the physicists in the second decade of the 21st century are adherents to the Copenhagen interpretation, thus giving them a plurality of opinion, there is a growing number of those who subscribe to the many worlds point of view. It should be noted also that there are a fair number of what are called interpretive agnostics, those who don't subscribe to a particular interpretation, preferring instead the adage, "shut up and calculate," first posited by physicist David Mermin. This view focuses on the pragmatic reality that quantum mechanics allows us to describe physical systems well enough to apply the techniques of calculation in ways that produce technologies as diverse as the microelectronics revolution and coherent light emission in stimulated systems, otherwise known as lasers. As an example, the transistor was invented at Bell Labs in 1952 as a direct application of quantum mechanics to a specific type of interface between 2 elements in their solid state, silicon and germanium. This invention really didn't depend on which of the several possible interpretations of what quantum theory means, just an ability to calculate the physical states of the systems at the interface. Of course, it is the method of building a super tiny on-off switch that allows trillions of single bits of information to be stored in ways defined by Boolean algebra to form a means of mass data storage and retrieval. As I've mentioned before, if you're listening to this podcast on a digital media storage device, whether that be an iPod or smartphone, the way in which the information that encodes my voice is stored depends on the applications of the principles of quantum theory. And while the transmission of that data is described by Maxwell's theory of electromagnetism, the devices which send and receive the information are built with quantum theories at their core. In our next episode, we'll return to the biography of Werner Heisenberg to look at his career during and after the Nazi regime in Germany, and his role in its scientific administration, including his work on atomic energy. So until next time, full sails on your journey.